dimension heat, all those things will be solving numerically. So before getting into the chapter, let's first recall what do you mean by a partial differential equation. A partial differential equation is the one that involves the partial differential coefficients. Suppose your f is a function of x and y. The partial differential coefficients are dou f by dou x, dou f by dou y, dou squared f by dou x squared, dou squared f by dou y squared, and so on, the first order, second order derivative. So any equation that involves the partial differential coefficients of the function, and remember the function should be depending on more than two or more independent variables, otherwise it becomes an ordinary differential equation. So such equations are called partial differential equations. Now we can see the general form of a partial differential equation. This general form involves all the independent variables. So any partial differential equation will involve all the independent variables, x1, x2, xn, the function u, their partial derivatives, second order, third order, higher order partial derivatives. This is the general form of a partial differential equation. In most of the cases, among the independent variables, our time parameter will also be included. In most of the cases, not always. Suppose you are in a steady state conditions, then t may not be a factor. So in almost all the cases, t will be one among the independent variables, and all other variables will be the spatial coordinates or the space variables in the space in which we are discussing. Now let's recollect what is the order of a differential equation. The highest order derivative in the given partial differential equation. Suppose you have dou cube by dou x cube and no higher derivatives are there, then the order will be 3. And most of the real life problems in our model can be modeled into second order PDE. So it's very important area of discussion. In many physics and chemical applications, we end up in the second order PDE. So solution to second order PDE is very important. Then we have the degree of a PDE. It's same as we define in an ordinary differential equation. Removing all the radical powers, that is 1 by 2, 1 by 3, all those things, we see to that all the powers are rational, natural numbers. Once rewriting the given equation such that all the powers are natural numbers, the degree of the highest order derivative will be the degree of partial differential equation. If the degree is 1 for each term, each term in the sense not for an independent variable, if your u and all its partial derivatives occur with the degree 1, then we call it as linear partial differential equation. Now we will see what is the general form of a second order linear partial differential equation. Here you can see u has appeared with degree 1, and the first order derivative dou u by dou x, dou u by dou y are also with degree 1. And the second order derivative, dou squared u by dou x, dou y, dou squared u by dou y squared, dou squared u by dou x squared are also of degree 1. So this can be taken as the general form of a partial differential equation. Now let's define what do you mean by quasi-linear differential equation. Suppose the terms contributing to the order of the differential equation are of degree 1, and the rest of the terms may be in any degree. Such differential equations are called quasi-linear differential equations. Now we are interested in discussing the second order partial differential equations. So here you could find all the second order derivatives are of degree 1, whereas our dependent function u, our first order derivatives and our independent variables may be of any degree. Such equations are called quasi-linear partial differential equations. We can classify these quasi-linear partial differential equations based on their discriminant value. The discriminant value is given by the coefficients of dou squared u by dou x squared, dou squared u by dou x dou y, dou squared u by dou y squared. if and it is b squared minus 4ac. Depending on the value of b squared minus 4ac, we can classify the given quasi-linear partial differential equation. If it is less than 0, same as the case we did in the second order, two-dimensional analytic geometry, if the eccentricity is less than 0, then the curve is elliptic, equal to 0 parabolic, greater than 0 hyperbolic. In the same sense, if the discriminant is less than 0, then the PDE is called an elliptic PDE. If the discriminant is equal to 0, then it is called a parabolic PDE. It's greater than 0, then it's a hyperbolic PDE. And already we have solved analytically the one-dimension wave, one-dimension heat, two-dimension heat under steady-state conditions. Now let's try to classify those standard PDE based on their discriminant values. That we'll be doing in the next slide. So some of the known PDE to us that we'll classify based on their discriminant value. Now the first one we have taken is the Laplace equation, or is the two-dimensional heat equation under steady-state conditions. Here the A value, that is coefficient of dou squared u by dou x squared, is 1. B value, that is coefficient of dou squared u by dou x dou y, is 0 because the term is absent here. And the coefficient of dou squared u by dou y squared is also 1. Therefore, b square minus 4ac, its value is going to be 0 minus 4 into 1 into 1 minus 4, which is less than 0. So our second two-dimensional heat equation under steady-state conditions is going to be an elliptic equation. The next one is the non-homogeneous equation, where we in the right hand side we have some non-zero function that we call as the Poisson equation. Here also A is 1, C is 1, B is 0. Therefore B square minus 4AC minus 4, which is less than 0. So it's an elliptic equation. Next we discuss the one-dimensional heat equation. Here already we saw in quasi-linear only the higher order terms, that is the terms that contribute to the order of the differential equation or degree of the differential equation alone play the role in classification. So we can leave dou u by dou t. Here A value is alpha squared, B 0, C 0. Therefore B square minus 4AC is 0. So the given PDE, that is the PDE representing one-dimensional heat equation, is a parabolic equation, parabolic partial differential equation. Similarly, now the next is the case of one-dimensional wave equation. So here again A can be taken as 1, C is minus A squared, and B is 0. Therefore B square minus 4AC is 4A squared. A being under the square term, it's always greater than 0. Also by definition in one-dimension wave equation, A square is tension by mass, is going to be a positive quantity. So 4A squared is always greater than 0. So this will be a hyperbolic partial differential equation. Next, let's see what do you mean by a solution of a PDE. If you wish, let's start from the ODE. Suppose you have dy by dx equal to cos x. What will be the solution to this equation? Any function y that satisfies the given differential equation will be the solution. So if you take y equal to sin x, or y equal to sin x plus 5, sin x plus 4, sin x plus 5, 6, or the solutions to the differential equation dy by dx equal to cos x. Similarly, any function that satisfies the given PDE in the space of the independent variable will be the solution to the partial differential equations. Now let's define what do you mean by harmonic functions. If the solution to the Laplace equation del squared of phi of x comma y is 0, all those solutions that are continuous, that have the continuous second order derivatives, are called harmonic functions. Next, let's see what do you mean by the Dirichlet problem. The problem of determining a solution U of a partial differential equation in a region R such that it should be a solution. So it has to satisfy the partial differential equations. And also in addition, it should satisfy all the given boundary conditions. Then the particular problem we call as Dirichlet problem. Ours, we are going to mainly discuss the Dirichlet problems where we'll be finding the numerical solution to the PDE numerically that satisfies the boundary conditions also. Now, how to evaluate the numerical solution of elliptic PDE? The entire session is divided into 3 parts. Yesterday, you would have discussed the numerical solution to ordinary differential equation. In this session, we'll try to complete the numerical solution to elliptic equations. In the next session, we'll be discussing numerical solution to parabolic differential equation, parabolic PDE and hyperbolic PDE. Now, let's see how to solve a Laplace and a Poisson PDE. To solve the elliptic equations, we first change the given PDE into a differential equations, difference equation. Okay, we'll replace the differential coefficients with the help of a difference coefficient. Suppose y is a function of x and y, sorry, z is a function of x and y, then the partial derivative dou z by dou x is going to be the limiting case of u of x plus h comma f of x plus h comma y minus f of x comma y by h. So that can be expressed in terms of a difference coefficient. Okay, such things are available in any basic material related to PDE. Now let's straight away get into what's the difference equations corresponding to the Laplace and Poisson equation. We know the Laplace equation is dou squared u by dou x squared plus dou squared u by dou y squared is equal to 0. So replacing the difference coefficients of dou squared u by dou x squared and dou squared u by dou squared u by dou y squared, we get the difference equation u of x plus h comma y plus u of x comma y plus h plus u of x minus h comma y plus u of x comma y minus h minus 4 times u of x comma y equal to 0. In the later part of the session, we'll be having the schematic representation of the same. Then you can easily understand. Next, the difference equation for the Laplace equation. And the only difference is going to be the right hand side. It's a non-zero function f of x comma y. So it's going to be u of x plus h comma y plus u of x comma y plus h. If you could visualize a mesh, you are at the point u of x comma y, then x plus h comma y will be the point to the right of u of x comma y. X minus h comma y will be the point to the left of u of x comma y. X comma y minus h will be the point below the point u of x comma y. And x comma y plus h will be the point above the point x comma y. So those things will be easily understanding while viewing in the schematic representation that you can do in the following slides. So in this, one important thing to notice, our u of x comma y depends on the neighboring points. That's the key thing we have to note down. The entire solution depends on this single factor. So to find the numerical solution in a region R, we divide R into a square mesh. The region in which we have to find the solution to the PDE, we divide that into a square mesh, each of side h. And the nodes in the mesh are called the mesh points. The representation of the mesh points we'll see in the later slides. So next, let's go through the algorithm. How to solve this elliptic PDE. So that's the first step we have seen earlier. Rewrite the given PDE as the difference equation. Once we have written the difference equation, applying the relation between the neighboring points and the mesh point, we get a system of linear equations which you can always solve by the known methodologies. Gauss elimination, Gauss Seidel, or by direct methods which you have learned in our lower classes, because all of them are going to be linear equations. If the variables are very minimum, we can go for direct elimination method, direct solution. Suppose we have got more number of variables, we have to seek the help of automation, that is systems, then it's better to have Gauss Seidel or Gauss Jacobi. So that's the third point we have done here. Each point, each mesh point will be expressed as the neighboring points in terms of the neighboring points and the PDE. And we'll be solving the resulting linear equations. This type of solution is called Liebman's method. Now let's see the schematic representation. Suppose this is the region R in which we have to find the solution to the partial differential equation. We divide this entire region R into square meshes. Here you can easily see the distance or the height along the x-axis is h. That is the space. They are equally spaced. 0, h, 2h, 3h, 4h. Similarly, along the y-axis also they are equally spaced. 0, h, 2h, 3h, 4h. And their intersecting points are the mesh points. P11, that is 1h, 1h. P21, that is along the x-axis 2h. Along the y-axis it is h, so it is P21. Next, let's relate these mesh values with the solution to our partial differential equation. So we can take the mesh points Pij as our solution to PDE at the point Pij, that is u of ih, jh. So making these substitutions in the difference equation we have already formulated, we get the relation for the Laplace equation to be ui plus 1 j plus ui plus 1 j is the point to the right, ui j minus 1 is the point below, ui minus 1 j is the point to the left, ui j plus 1 is the point above our point u of I j. Using this relation, we'll be formulating a set of linear equations which we'll be solving, and you'll be easily able to follow this once we start solving the problems. And this will be the difference equation representing the Poisson equation. Now let's see the schematic representation. This is your u of I j, whose value depends on ui minus 1 j, ui plus 1 j, ui j minus 1, I j plus 1. In the process of solving, at times we'll also be using the diagonal 5-point formula, which is given by this. Now let's start doing the problems. The first problem of discussion is going to be the solution of Laplace equation. The question reads this way. Evaluate the differential equation u of x y satisfying the equation, the Laplace equation, del squared u is equal to 0 at the lattice points, given the boundary values as follows. Given the boundary values as below. So in the question we have given a mesh the boundary values are also given. The values at the point of the boundaries are 1000, 2000, 2000, 1000, 1000, 1000, and this boundary value is also 1000, and the next boundary value is given as 500, 0, and these values are 0, 0, 500, and we are asked to find the solution to this PDE. That is, we have to find the values at these mesh points U1, U2, U3 and U4. The first thing we shall see is whether we can apply the 5-point formula, standard 5-point formula or diagonal 5-point formula. If you take this U1, the diagonal 5-point formula involves 1000, the point above, below, point to the left and point to the right. But the values U2 and U3 are not known. So we get a linear equation. So these things are given in the question. So if you wish to solve such a PDE, the solution to this PDE is to find the value of U1, U2, U3 and U4 satisfying this, whose boundary conditions are this. So at U1, and if you wish, you can take down this difference equation representing the Laplace equation. As we have seen in the few minutes ago, the difference equation is ui comma j plus 1 plus ui plus 1 comma j plus ui comma j minus 1 plus ui minus 1 comma j minus 4 ui comma j is equal to 0. This is the difference equation corresponding to the Laplace equation. From this, we find ui comma j is equal to 1 by 4 times the neighboring points ui comma j plus 1 plus ui plus 1 comma j plus ui comma j minus 1 plus ui minus 1 comma j. So applying these conditions, take this point. This is u, to be very precise, it is u1, 1 comma I is equal to 1 and j is equal to 2. These are the j values. In the y direction, we have j values 0, 1, 2, 3. This is the direction of y, that is j. And in the direction of x, we have the I values 0, 1, 2 and 3. So at u1, it is u1 comma 2. So you put I equal to 1, j equal to 2, and that is going to be the standard 4-point formula. So u1 is equal to 1 by 4 into ui comma j plus 1. It is 1000 plus ui plus 1 comma j, that is u2 plus ui comma j minus 1, it is u3 plus ui minus 1 comma j, that is point to the left, that is 2000. So on simplifying, we get the equation 4u1 minus u2 minus u3 is equal to 2000. Let's call it as equation 1. Similarly, at the point u2, again applying this relation, we get u2 is equal to 1 by 4 into the point above ui comma j plus 1. It is the point above u2, that is 1000, plus ui plus 1 comma j, that is point to the right hand side, which is 500. Then we have ui minus I comma j minus 1, that is point below, that is u4, plus point to the left hand side, that is going to be u1. So from this, rewriting this equation, we get u1 or 4u2. We have 4u2 minus u1 minus u4 is equal to 1500. This is equation 2. Next, at the point u3, we have applying the same schematic representation. u3 is equal to 1 by 4 into point above u3, that is u1, plus point to the right of u3, that is u4, plus the mesh point, value at the mesh point below u3, that is u500, plus the value at the mesh point to the left of u3, that is 2000. So from this, we get the equation u4 u3 minus u1 minus u4 equal to 2500. Call it equation 3. Next, we take the point at u4. From the representation, u4 is equal to 1 by 4 into point above u4, that is u2, plus point to the right of u4, that is 0, plus point to the left of u4, that is u3, plus point below u4, that is 0. So from this, we get 4 u4 minus u2 minus u3 is equal to 0. Calling it, name it equation 4. Now it's the usual way of elimination. We can find u1, u2, u3. We have got all the 4 equations. Now first reduce it into 3 equations, 3 unknowns. So reducing into 3 unknowns, we get the following equations from equation 1, 2, 3 and 4. And on simplification, we get u2, we get set of equations, which on solving we get u1 is equal to 1195, u2 is equal to 745, u3 is equal to 445, and u4 is equal to 1035. In most of the recent calculators, you can directly enter the coefficients in the equation mode. You can choose ax plus by plus cz plus d equal to 0, or dw equal to e. In this mode, you just can enter the coefficients and solve the equations. On solving, you get u1, u2, u3 and u4. Let's discuss another problem in the Laplace equation. The problem reads this way. Solve uxx plus uyy. But in this problem, we are not given the mesh. Instead, we are given a set of boundary conditions over the square mesh of side 4 units. Satisfying the following boundary conditions. Satisfying the following boundary conditions. The first condition is u of 0, y is equal to 0 for all the y values between 0 and 4. The second condition, u of 4, y is equal to 12 plus y, again for all the y values between 0 and 4. And third one, u of x, 0 is equal to 3x for 0 less than or equal to x less than or equal to 4 for all the x values within that range, and u of x, 4 is equal to x squared for all the x values between 0 and 4. Now let's try to construct the mesh of side 4 units each. So we have x equal to 0, 1, sorry, y0, y1, 2, 3 and 4. This along the y-axis. Y is equal to 0, 1, 2, 3 and 4. Similarly, along the x-axis, x equal to 1, x equal to 2, x is equal to 3 and x is equal to 4. So the x-axis, we have x is equal to 0, sorry, 0 is already there. This is x equal to 0, 1, 2, 3 and 4. Now let's fill up the boundary conditions. When x is equal to 0, u is equal to 0. So x is equal to 0 is this boundary. So the value of u at all these mesh points, x equal to 0, y equal to 0, 0, 1, 0, 2, 0, 3, 0, 4 are all 0. Next, the value at the mesh points x is equal to 4. These are the mesh points having x is equal to 4. This is 4, 0, 4, 1, 4, 2, 4, 3, 4, 4. So here y is equal to 0. So 12 plus 0, it is 12. The mesh value at this point is 12. And the mesh value at this point, y is equal to 1. So 12 plus 1, we get 13. And this point is, at this point, x is equal to 4, y is equal to 1. So substituting y is equal to 1 or y is equal to 2. Substituting y equal to 2 here, get 12 plus 2, it is 14. Similarly, here y is equal to 3, so 12 plus 3, 15, 12 plus 4, 16. Now, the next boundary condition. When y equal to 0, the boundary values are 3x. These are the points where we get y equal to 0. So here y equal to 0, x is equal to 1. So 3 into 1, 3. X is equal to 2. So 3 into 2, 6. X is equal to 3. 3 into 3, 9. X is equal to 4. 3 into 4, 12. Similarly, the next condition is when y is equal to 4. Along this mesh line, we have y is equal to 4. And the corresponding u value, the mesh point value is given by x squared. So at this point, it is x squared. Here the x value is 1. So 1 squared, 1. Here x squared, x value 2. So 2 squared, 4. X squared, x value 3. So 3 squared is 9. So this boundary condition also we have represented. The solution to this equation is, that is, our aim is to find the value at these mesh points u1, u2, u3, u4, u5, u6, u7, u8 and u9. So we have to find the value at these mesh points. We apply the same standard 5-point formula to get these mesh values, but that will result in 9 linear equations which we cannot solve manually. So what we do is, instead of framing an equation, let's in case of 9 points, the Liebman's iteration says, first we'll be computing the points to which we can apply the standard 5-point formula. So if you take, so first you apply standard 5-point formula to U5. So at U5, this is going to be the solution part. We have just done with constructing the mesh for the given boundary conditions. At U5, if you take U5, the 4 neighboring values are not known. That is U2, U4, U8 and U6 are not known. But you move one step ahead. But we know these 4 points. So we can apply standard 5-point formula to U5. So we have U5 is equal to 1 by 4 into the point above, the known value above U5, that is 4, plus the known value to the right of U5. Remember, all these points should be at equal distance. You have removed 2 points above. So 2 points to the right, we get 14, plus 2 points below, 6, plus 2 points to the left, 0. So we have got the initial value for U5 to be 6. Similarly, now go for any other point at which we can apply the standard 5-point formula. If you choose U2, we cannot apply standard 5-point because we don't know U1 and U3. If you go to U1, we cannot apply standard 5-point because we may not be knowing U2 and U4. But we can apply diagonal 5-point formula to this U1. If you take U1, the diagonal values are 4, 7, U5 and 2. All these values are known. So at for U1, we apply the diagonal 5-point formula. In the previous case, we applied standard 5-point formula. Now let's apply the diagonal 5-point formula. So U1 is equal to 1 by 4 into the values along the diagonal 4 plus 4 plus U5. U5 we have found as 6 plus 0. So it is 14 by 4, that is equal to 2.5. This we have got by applying diagonal 5-point formula. Next, at the next point, U3. For U3 also, we can apply the diagonal 5-point formula. Because the diagonal values, all the diagonal values are known, we can apply diagonal 5-point formula. So at U3, we have U3 is equal to 1 by 4 into the values along the diagonals 4 plus 16 plus 14 plus U5, that is 6, and this works out to be 10. This we again got by applying diagonal 5-point formula. So far, now let's try to apply the diagonal 5-point formula to U6. So at U6, we have U6 is equal to 1 by 4 into sum of the diagonal values, that is 0, 0 plus U5, it is 6 plus 6 plus 0, that is equal to 3. This again we got by applying the diagonal 5-point formula. Next we go for U9. So at U9, applying the diagonal 5-point formula, we have 1 by 4 into the diagonal values. The diagonal values at these points are U5, which is 6. 6 plus 6 plus 14 plus 12 plus 6, and its value is going to be 9.5. This again by applying diagonal 5-point formula. So far we have computed the values. First, initial values for U1, U3, U5, U6, U9. So all these orange mesh values and the violet mesh values are known. So the current unknown values are going to be U2, for which all the 4 neighboring values are known. U4, again all the 4 neighboring values are known. And U6, for which all the neighboring values are known. So we can apply diagonal 5-point standard 5-point formula to find U2, U4, U6 and U9. So for the remaining cases, we apply standard 5-point formula. Whenever we have the convenience of applying standard 5-point formula, we apply standard 5-point formula. Only if it is not possible, we go for diagonal 5-point formula. So at U2, by applying the standard 5-point formula, we get U2 is equal to 1 by 4 into 4 plus 10 plus 6 plus 2.5. That is equal to 9.5. Similarly, at U4, only these 4 values are missing. So U4 is equal to 1 by 4 into value to the left of U4, that will be, U4 is known. So we just need U6. U4 also we need. Yes, we need our U4 also. U4 is equal to 1 by 4 into value to the left, that is 0, plus value to the right, that is going to be U5, which is 6, plus value to the above, that is U1, which is 2.5, and the value below is U7, which is equal to 3. So this value is going to be using the calculator. Let's get this value. 11.5 divided by 4, that is equal to 2.875. Next, we get the value at U6. At U6, you again apply the standard 5-point formula. Value above U6, that is U3, which is equal to 10, plus 14, value to the right, 14, plus value below 9.5, plus value to the left, it is 6. So it works out to be 9.875. And that final value at U8, we have U8 is equal to 1 by 4 into value above U8, it is going to be U5, that is 6, plus value to the right is U9, that is 9.5. Value below, it is the boundary value, that is 6. Value to the left, it is U7, that is 3. So this works out to be 6.125. So we have got all the initial values. So now in the mesh, we know the initial value for all the 9 points. U1, U2, U3, U4, U5, U6, U7, U8, U9. So we just have to get, we have to iterate the process until the successive values are equal. So now in each case, we apply the standard 5-point formula. Standard 5-point formula for U1, U2, U3, U4, U5, and we get the solution. After 3 iterations, we get U1 is equal to 2.37, U2 is equal to 5.59, U3 is equal to 9.87. Hello, sir. the வரேன் சார் ஒரு நிமிஷம் சார் அந்த ஒரு நிமிஷம் சார் இதோ பார்க்குறேன் சார் எனக்கு இங்கே எதுவும் தெரியலையே சார் போயிட்டு இருக்கு சார் எஸ் சார் ஓகே சார் yes sir surely sir yes sir கொடுத்துட்டேன் sir yes sir so at each of these points initially we have got the initial values for u1 u2 u3 u4 u5 now so we iterate the values again at we know all the neighboring values of u1, that is we got the initial value for u2 u4. Similarly, when in the case of u2 we know the neighboring values u1 u3 u5. So at each mesh value we know all the neighboring values, so we can apply the diagonal standard 5-point formula repeatedly until the successive iterations are all equal. So at the end of 3 iterations we can find the values as u4 it is 2.88, u5 to be 6.13, u6 to be 9.88, u7 to be 3.01, u8 to be 6.16, u9 to be 9.51. That is, from the initial values we have to compute the successive approximations. For example, your u1 is going to be applying the diagonal standard 5-point formula. It is 1 by 4 into 1 plus u2. u2 we have calculated earlier. The initial value is 5.625 plus u4. The initial value for u4 is 2.875. 2.875 plus value to the left, that is going to be 0. So this will be the first iterative value. Similarly, you get the value for all the mesh values for the first iteration. Then go for second iteration, third iteration, fourth iteration, and so on until the successive iterative values are equal. And these are the values we arrive at the end of 3 iterations. If you have any difficulty in doing these problems, you can post this in a Google Classroom, which we will be creating in short. In the next class, let's discuss the Poisson equation and other parabolic and hyperbolic equation. There is also a case where the boundary values may be symmetrical. If you construct a mesh, you may arrive at a situation where the boundary values may be symmetrical. This is one such problem. Third question. Solve the Laplace equation for the following square mesh given the square mesh. The boundary values are 1, 2, 1, 2, 4, 5, 4, 5. And we are asked to find the mesh points U1, U2, U3 and U4. So if you fold the mesh along this line, just fold the mesh along this line. So these boundary values will exactly coincide with these boundary values. And this set of boundary values will coincide with this boundary value. So we can say it is the mesh values are symmetric about this line. So that says your U3 should coincide with U2. So we can claim U2 is equal to U3. But if we fold along this line, try to fold along this line, the boundary values do not coincide. So U1 is not equal to U4. So now we can formulate the equations and solve them. So if you take U1 is going to be 1 by 4 into the points along the apply the standard 5-point formula. Or one thing we can do, we'll get a set of linear equations which we have to solve. So let's go by that. It is going to be 1 plus U2 plus U2. It is 1 plus U2 plus U3, but U2 is equal to U3. So we have got this value. We end up with this value. So we have 4U1 minus 2U2 is equal to 2. Similarly, at U2, we have 1 by 4 into the 4 neighboring points, U1, that is U1 plus point above 2 plus point to the right 4 plus point below U4. So this implies 4U2 or minus U1 plus 4U2 minus U4 is equal to 6. Similarly, at the point U4, because we need to calculate only U1, U4 and U2, because U3 is same as U2, we formulate 3 equations in U1, U2 and U4. So at U4, it is going to be 1 by 4 into point to the left U3, which is nothing but U2, plus point above, it is again U2, point to the right 5, plus point below, it is also 5. This implies 4U4 minus 2U2 is equal to 10. So on solving these 3 equations for the unknowns U1, U2 and U4, we get U1 is equal to, the solution at the mesh points is U1 is equal to 2, U2 is equal to U3 is equal to 3 and U4 is equal to 4. So we'll discuss more problems on Poisson equation and hyperbolic and parabolic equations in the next session. Thank you.